Hi, welcome back to the lecture series on MMTC 202. We continue this lecture, the previous lecture, which is on upper functions. So we have in the previous lecture we have seen certain properties of upper functions. Not today again. We'll see some other properties of upper functions. First, we will discuss the following remark on upper functions. Let's see this remark. So remark is if f is an upper function, f is greater or equal to 0. If f is an upper function, if f is an upper function and f greater or equal to 0 almost everywhere, then there should exist, then there exists a sequence phi n of step functions such that this phi n is greater or equal to 0. It's a non-negative sequence almost everywhere, and this sequence is approaching to this f, increases to f. The proof is very simple. It's not too hard. Since f is an upper function, f is an upper function. So therefore by definition of upper function, therefore there exists a sequence psi n of step functions such that this psi n, it increases to f almost everywhere, which implies psi n plus increases to f plus the positive part of f, which is equal to f, because f is a non-negative function almost everywhere. So that implies that this phi n increases to f almost everywhere, where, or what is this phi n? Phi n is equal to psi n plus, which is greater or equal to 0, because psi n plus is always greater or equal to 0. And it's also a step function. So thus we have a sequence of step functions phi n, which is greater or equal to 0 almost everywhere, and that sequence, it's increasing to f, because this psi n plus is again an increasing sequence. So this proves the remark. Now next we have following theorem. This theorem precisely states that a limit of a sequence of step functions, limit of a sequence of upper functions is again an upper function with some conditions. Let's first state this theorem. We'll see its statement first. So let f be a function. Let f from let f be a function from x to r. Okay, and let's take this sequence fn. Sequence fn of upper functions such that it's increasing sequence and it increases to f almost everywhere. And one more condition, limit of integral of fn, because integral of n step function is already defined. Limit of integral of fn is finite. Then we show that then this f is an upper function. Then f is an upper function. Proof. Since for each I greater or equal to 1, fi is an upper function. Fi is an upper function. So for this fi, we can find a sequence of step functions. Thus, thus there exists a sequence of phi and I of upper functions such that this phi and I, it increases to the upper function fi. There exists a sequence phi and I of step function, not upper functions. fi fi is an upper function. For this upper function, we have a sequence of step functions. Okay, step function. Okay, it is a sequence of step functions such that phi and I increases to fi almost everywhere. So also this also limit of integral of phi and I and approach to infinity is finite. Okay, so each fi has a generating sequence. So let's suppose that phi and I and runs from 1 to infinity is the generating sequence for fi. Now we define for each and define we have to construct the sequence of step functions for f, generating sequence for f, because we need to show that f is an upper function. So for each and let's define that sequence for each and define psi n, which is equal to join I runs from 1 to n phi and I. Then this psi n is a sequence of step function, is a sequence of step functions. Okay, is a sequence of step function. This is a trivial. We show that it's a generating sequence. We show that this psi n is a generating sequence for f. So first we know that limit of psi n is same as limit of fn actually. First we show that this limit of psi n is equal to limit of fn, and limit of fn is equal to f. First we show that this limit of psi n is equal to f. For this we show that limit of psi n is same as limit of fn, and limit of fn, it is given that limit of fn is equal to f. So let's verify this. We have what's this limit of psi n approach to infinity. Since psi n is an increasing sequence, this limit it is actually the join. It's join k runs from 1 to infinity psi k, and that psi k it's equal to limit. It's join k runs from 1 to infinity. What is psi k? It's a join I runs from 1 to n. I runs from 1 to k. Sorry, I runs from 1 to k phi ki. Okay, name it first. Now we find the limit of now limit n approach to infinity fn. What's this limit? It's again the join, because it's an increasing sequence. It's a join k runs from 1 to infinity fk, and that's equal to join k runs from 1 to infinity. What's fk? Fk is the join n runs from 1 to infinity phi k. What's the reason for this? Because this phi and k, it increases to fk. Okay, limit is with respect to k. Phi and k increases to fk. So that means the join of phi and k with respect to n, it's fk actually. Okay, so this one, this we can interchange, we can change the values of n. We can write this as join n runs from 1 to infinity, then join k runs from 1 to infinity. We can interchange the values of k and n. It's 5 k. So there is no harm to change this notation. But now this one, it's equal to limit and approach to infinity, join I runs from 1 to n, okay, then join k runs from 1 to infinity phi kn, okay, this is okay. This is equal to, now we change, we replace these this join and this join. This is limit and approach to infinity, uh, k runs from, join k runs from 1 to infinity, then join I runs from 1 to n, that it's phi k n, okay, phi k n, phi ki, sorry, it's phi ki, because I runs from 1 to n, it's phi ki, sorry, it's phi ki here, it's not phi k n, it's phi ki. I is running from 1 to n, okay. It's phi ki. Here it's phi ki, okay. Here it is phi ki. Now this one, what's this? This is actually, by first you can see this is by first here we have this one, k runs from 1 to infinity, I runs from 1 to k, phi ki, I runs from 1 to k, phi ki, I runs from 1 to k, I runs from 1 to n, not 1 to k. It's again here I runs from 1 to k, psi k, psi, this is psi k, k runs from 1 to infinity, but that psi k is equal to I runs from 1 to k. This I runs from 1 to k actually, not I runs from 1 to k. Okay, here I will change it. It's k approaches to infinity actually. This is here I runs from 1 to k, k approaching to infinity. Can I do this? K runs from 1 to infinity. Okay, this is I runs from 1 to n phi ki. So I will write here k approaching to infinity. K is approaching to infinity. Okay. If I will change it, if I want to change this actually here, it's phi ki, phi ki. I runs from 1 to k. It should be 1 to k. 1 to k, okay. So here I want to change here, but this is a iron some 1 to k. This is limit of k actually here. Okay, so I will change this here. It's k approach to 1 to infinity. Iron is from 1 to k. Okay. First k runs from 1 to infinity. Then this can be done. Okay, this is I runs from 1 to k. First you apply this k runs from 1 to infinity. Then this limit, actually this limit now, there is no role of this limit now. can see k runs from 1 to infinity. It's equal to, this is equal to, this is same as limit of psi. You can see here. This is same as limit of by 1. Okay, you can see here. By 1, this is same as limit of psi. Limit of psi is this k runs from 1 to infinity, because its k is approaching to infinity, but k runs from 1 to infinity. I runs from 1 to k. If you vary I runs from 1 to k, then you take k approach to infinity. This is same as join k runs from 1 to infinity, join I runs from 1 to k phi ki, and that's equal to this limit. That's equal to limit and approach to infinity. Is it sine or phi? By 1, it's sine. Okay, this is a sine. Okay, by 1. So thus limit of psi n is same as limit of fn. So both the limits are actually same. Both the limits are actually same. And but the limit of fn is equal to f. So this implies psi n increases to f. So we need to show that psi n is the generating sequence for f. So this is the first condition for generating sequence, for f to be a generating sequence. So next, one more property that we need to verify, which is a limit of integral of psi must be equal to finite. So let's verify that property now. Okay, so we have this. Now we verified that. Now we verify that. Now we verify that psi n is less or equal to fn almost everywhere. Let's verify this one. Psi n is less or equal to fn almost everywhere. So what's psi n? We have psi n, which is equal to phi n1 join phi n2 join phi nn, and phi n1 it's less or equal to f1, because a limit of phi n1 is equal to f1, and it is an increasing limit, and this is less or equal to f2 join so on join, this is less or equal to fn, as phi nk increases to fk. It's true for all k greater or equal to 1. So which implies phi and k is less or equal to fk, k greater or equal to 1, because it is an increasing limit. So this means each term of the sequence must be less or equal to the limit, and limit is fk. Okay. So for all k greater or equal to 1, this phi n k is less or equal to fk. That means this phi n1 is less or equal to f1, phi 2 is less or equal to f1, so on and so forth. Now this is the join, but again this fn, it is an increasing sequence. So this join of these f1, f2, fn, because fn is greater or equal to each term of this join. Fn is greater or equal to f1, fn is greater or equal to f2, and up to fn minus 1. So this join is equal to actually fn. So that means psi n is less or equal to fn. The limit of psi n is same as the limit of fn, but this psi n is always less or equal to fn. That's condition here. Okay, so psi n is less or equal to fn. That we have verified. This implies, consequently, this gives the limit of integral of psi n is less or equal to limit of integral of fn, which is finite. It's given. So that means this psi n is a generating sequence, is a generating sequence for f, and hence f is f is an upper function, hence f is an upper function. So which proves that our f is an upper function. Now we show that limit of integral of sine is same as limit of integral of f, and okay. Now we show that now we show that this limit of integral is actually equal to limit of integral of sine, and that's equal to integral of f by definition of an upper function, integral of an upper function. So we verify this one. We have seen that limit of integral of sine is less or equal to limit of integral of f, but we need to prove that actually equality holds. So for this, we have for each fixed I, phi n I is less or equal to fn sine. For each fixed I, phi n I is less or equal to psi I, because psi I is the join actually, because psi I is join. So that phi n I is less or equal to fi for all n greater or equal to, for all n greater or equal to I. You can easily verify this. So this is not too hard to verify. So this is true. It follows that it follows that integral of fi is equal to, which is equal to by definition of an upper, because fi is an upper function and phi and I is the generating sequence for fi. So by definition of integral of fi is equal to this limit, but this is less or equal to psi I, which is less or equal to limit, which is less or equal to limit n approach to infinity sine, because in particular this I is equal to n. So this is less or equal to limit n approach to infinity integral of sine, So this is less or equal to this for each fixed I greater or equal to n. So we can apply the limit. For I. So that means limit of integral of f. We can replace I by n again, because I is approaching to infinity on this side, and on this side n is approaching to infinity. So we can choose the same numbers, because both are approaching to infinity and both are positive integers. This is less or equal to limit of integral of fn, and this sorry, it's sine on this side. Sorry, it's sine on this side, not phi. On this side we have sine. Okay. So here it's sine. Okay, sine and sine. And the reverse inequality is already established, so therefore equality holds. So this thus limit of integral of fn is same as limit of integral of sine, and which is equal to integral of f. So this proves the theorem completely. Now we have last theorem of this section, upper functions. Which states that if fn is a sequence of upper function, if fn is a sequence of upper functions, if fn is a sequence of upper functions, such that fn decreases to 0, such that fn decreases to 0 almost everywhere, the limit of the integral is 0, then limit of integral of fn is equal to 0. Proof. Proof. So this fn, so first I want to mention here that If f is an upper function, if f is an upper function, then we can find a sequence of then there exists a sequence of sine of of step functions such that sine increases to f almost everywhere, and this I want to use on the sequence fn, because fn is also a sequence of upper functions, and limit n approach to infinity, integral sine is equal to integral of f, and this is finite. So this limit is finite. Okay, so therefore for each epsilon positive, therefore for all epsilon positive, we can choose n such that we can choose we can choose n such that this limit such that integral of fn minus integral of f, sorry, integral of f integral of f integral of f minus integral of psi m, suppose it's modulus, but we don't need to take the mod, because this is increases to f, so that means integral of f is always greater or equal to integral of psi n for each f. This is less than epsilon for all m greater or equal to, and that's the definition of limit. In particular, this is true for n. So this implies integral of f minus integral of psi n is less than epsilon for all n, not for all n, no, because I have fixed this m is equal to n. Okay, so this is true for upper function. If f is an upper function, then for each epsilon positive, I can find a step function psi n such that integral of f minus integral of psi n is less than epsilon. Now, it is given that fn is a sequence of upper function. Therefore, for that fn, we can find a step function phi n such that integral of fn minus integral of phi n is less than epsilon. And here, in that case, in our case, I will choose epsilon as epsilon into 2 power minus n. Now since fn is an upper function, and let epsilon be a positive number, choose a step function, choose a step function phi n such that 0 less or equal to phi n less or equal to fn, obviously less or equal to fn. Why it's 0 less or equal to fn? Because fn is greater or equal to 0, because fn it decreases to 0, so that means fn is greater than 0 actually. So whenever we have a non-negative upper function, then I can find the non-negative step function. This is already done in one of our theorem. So this is non-negative also, and it is also less or equal to fn. That's because it is increases to fn. That sequence is actually increases to fn. So I can find for each epsilon positive, I can find a step function phi such that this and this one holds. This is here almost everywhere. Okay, and this integral of fn minus integral of phi is less than epsilon into 2 power minus n. Okay, now this minus fn minus phi is an upper function, because this implies this integral of fn plus integral of minus phi n less than epsilon into 2 power minus n. Now this is an upper function because phi n is a step function, therefore it's minus times a step function is again a step function, hence an upper function. This fn is an upper function, and sum of integral of upper function is like it's already done. It's fn minus phi n less than epsilon into minus 2 power. The condition for that is the following, that these functions must be upper functions. Here fn is upper function, minus phi n is also an upper function. Negative times upper function need not be upper function, but it is here negative times the step function, which is again a step function, and every step function is an upper function. Okay. So this is true. Now let's choose cyan. let cyan is equal to the meet I runs from 1 to n phi I. Let's choose cyan this for each n. For all n greater or equal to 1. Then cyan is a sequence of step functions. Then this cyan is a sequence of step functions, is a sequence of step functions satisfying zero less or equal to cyan, obviously less or equal to cyan, because it's non-negative, as finals are non-negative, so meet of non-negative functions is again a non-negative function, and it's also decreasing, because if you increase the values of n, this will decrease, because you are taking the minimum of more functions. Okay, this is a decreasing sequence. So also this holds. Also cyan decreases to 0. Why cyan decreases to 0? Because cyan is less or equal to fn, and fn decreases to 0. This decreases to 0. So cyan is non-negative, and it must decrease. It cannot be negative actually. Limit of cyan cannot be negative. So limit of cyan must be equal to 0, because cyan is non-negative function, but it is less or equal to fn, whose limit is 0. And limit of this cannot be negative, so therefore it must be equal to 0. It must be equal to 0. So cyan decreases to 0, which implies that its integral must be equal to 0, because for step function we had done this result. If the sequence of step functions decrease to 0, then the limit of the integral must be equal to 0. Then the integral of cyan must be equal to, this must approach to 0 for step function, not for upper function. Now we need to, in this step, we need to prove the same result for upper functions actually. Okay, this limit is 0. This limit is, now we apply the definition of limit. Epsilon is already fixed. Epsilon is already there fixed. So limit of integral of cyan is 0. So we choose k such that integral of cyan is less than 0, is less than epsilon for all n greater or equal to k. This is the definition of limit, because limit of cyan is equal to 0. So limit of integral of cyan minus 0 must be less than epsilon for all n greater or equal to k. That's the definition of limit. Now we have following almost everywhere inequality. Now we have the following. We have the following almost everywhere inequality, which is a 0 less or equal to fn minus cyan, because fn is greater or equal to cyan, so it must be greater or equal to 0 almost everywhere, and which is equal to fn minus cyan. What's this cyan? It is giant. We meet I runs of 1 to n phi I. Okay, and this fn it's equal to the meet I runs from 1 to n fn. Okay, because can take the meet with respect to I. It's the same as, because each in this meet, each term is equal to fn. It is fn meet n times, which is equal to fn minus join I runs from 1 to n phi I, and this is equal to me join I runs from 1 to n fn. This will be plus, then it will be here meet I runs from 1 join I runs of 1 to n minus times phi I, because join of minus is equal to minus meet. That's simple. That's simple. And this will be equal to, now this is equal to join I runs from 1 to n fn minus phi I, fn minus phi I, which is less or equal to, which is less or equal to, which is less or equal to, join I runs from 1 to n. So basically, if I replace fn by fi's, now I change, and this the one of the term in this join is fn minus phi I also. So this obviously it's less or equal because you are adding functions. You are taking now join of f1 minus phi 1, f2 minus phi, and so on and so forth. Here you have the join of fn minus phi 1, fn minus phi 2, so on up to fn minus phi n. And here you have the join of f1. So one of them is one of the function is this one. Okay, this here it is fn minus phi n is also, it includes fn minus phi n also. So this is a lesser equal to, yeah, or you can say this join of fn I runs from 1 to n lesser equal to join of fi I runs from 1 to n. That's simple. So this is always lesser equal to this, and which is equal to, this is now this is lesser equal to, if I will add all the terms, because because it's a NAS, it's a join of non-negative terms. So if I will add, it's this sum must be lesser, greater or equal to, this sum must be greater than, it's 5 here. It's like this, you are taking suppose maximum of 2 and 3, that's equal to 3, but this maximum of 2 and 3 is always lesser equal to their sum. It's like that. So you are taking maximum of n numbers, they are all non-negative numbers, and this the maximum of these n numbers will be lesser equal to sum of these n numbers. It's like that. Okay, so this is trigger, this is trigger, this is equal to sum, this is equal to sum. So this implies, so now what we have achieved here, so that is we have achieved the following, that is a 0 less or equal to fn minus phi n, and it's less or equal to summation I runs from 1 to n, I runs from 1 to n fi minus phi I. Okay, fi minus phi I. So this is this we have done here. So now let's apply the integral, and it's obviously non-negative. 0 less or equal to integral of fn minus integral of phi n. This is already done. We can separate the integrals because both are both fn and minus phi n, they are both upper functions actually. So that's simple. This can be done for upper functions, and this is less or equal to integral of this, which is the summation, which is summation I runs from 1 to n integral of fi minus integral of phi I. Okay, this is less, and this difference is less than, it's less than this difference I runs from 1 to n f1 integral of f1 minus phi 1 integral of f2 minus phi 2, or integral of f1 minus phi 1 integral of f2 minus phi 2. This sum, this each term is less than epsilon times summation I runs from 1 to n 2 power I, which is strictly less than epsilon times the infinite series I runs from 1 to infinity 2 power I, that's equal to epsilon because that series is equal to 1. So this is this sum so this fn minus integral fn minus integral phi, and it's less than epsilon. This is here actually. This is done here where it is where we have done it. This, look at this, integral of fn minus integral of phi n is less than epsilon times 2 power minus n. This we have applied here actually, epsilon times 2 power minus n. Okay, this, so this is less or equal to epsilon times 2 power minus I, 2 power minus I, sorry, it's 2 power minus I. So that sum is equal to 1, it's less than now epsilon. So this means 0 less or equal to integral of fn minus integral of phi n, which is less than epsilon, okay, which is less than epsilon for each epsilon positive, so which implies 0, which is less or equal to in limit integral of fn, because it's non-negative sequence, and this is less than epsilon plus integral of phi n, integral of phi n, integral of sorry, it's integral of psi n here, it's not phi n, oh sorry, it's not phi n, it's not phi n, it's sin on this side. Integral of this is fn minus sin, it's fn minus sin. So this is actually fn minus sin, not fn minus phi n. Okay, this is fn minus sin, fn minus sin. Okay, this is fn minus sin, fn minus sin. This is here integral sin. Now the next page, it's again sin here, not phi n. It is sin here. This is here sin. Okay, so this must be here sin. This is integral sin. This is a psi n here. Okay, psi. So 0 less or equal to integral fn, which is less than epsilon plus integral psi, integral psi. But integral psi n and greater or equal to k, it's less than epsilon. So this is less than twice epsilon for all n greater or equal to k. So that means this limit, this is less than twice epsilon for all n greater or equal to k, and it's also greater or equal to 0, which implies limit of integral of fn must be equal to 0. So that proves this theorem completely. So now in the next lecture, we'll discuss integrable functions. Okay, because as we have seen that the collection of upper functions is not closed with respect to the negative multiplication. So in order to make this collection as vector space, so we must have one thing, that it should be closed with respect to each scalar multiplication. So for this, we take the collection of integrable functions. So what are the integrable functions actually? They are we define integral function as the difference of two upper functions. If u is an upper function, v is an upper function, then we call u minus v is an integrable function, and we will see this collection of all such functions u minus v, where u is an upper, v is an upper, this collection is closed with respect to scalar multiplication and also addition, and it will form a vector space. So that will give a nice structure. Now this collection of all integrable functions will be a vector space. So that we'll discuss in the next lecture. Thank you.